still hiring. I will talk about that, what are the positions we are hiring, and if there are some master students who are interested to do some serious research, please feel free to contact with me, right? So out of the 5 PhD students I have here, I actually have quite some students that I recruit from the master students at WPI, and they are all doing a very good job here. Okay, so, all right. Okay, and my group is actually pretty active on research. One parameter to tell that is about the journal publications. So far we have 14 papers, submitted, outside in this year, and 9 of them already got published or accepted. So if you are interested, you can check our website to see the latest published work. All right, okay, so as I said, my group, the name I gave is IMPD. So the reason I gave that is from the sketch I show here. This is because I used to work in industry, and this is what I realized. So when you work in industry, I hope most of you actually after graduation will also go to industry. You will realize that you will have supervisors. Okay, they will not do detailed research, but they care about your delivery, right? So the delivery they care will be about either the performance or properties, and typically you will be the guy to do the detailed research, right? Especially in your early career. So what we have figured out is like the thermodynamics and kinetics actually play a critical role, right? Actually, it's a core of the either materials or process design, right? So you need to work on those, and then the material or process you design can meet the performance or property requirements. And we have figured out this is kind of like a unique the general approach, right? That you can use in a lot of different materials. So that is why we working on a lot of different materials, right? Like we have working on alloys, right? Back in my PhD study, I work on magnesium alloy. I have also working on steels. And recently, right, this talk will be about the high entropy alloy. My group also have extensive research on ceramics. So we have 2 types of ceramics that we're working on. One is the structural ceramics, like zinc carbide, boron carbide, those kind of things, right? And also the functional ceramics, like SFC, SOEC, OTM, lithium battery, all those things. So I will talk some of those later today. And also we have some hobby, like to working on what is happening for nanomaterials, right? Okay, so all of this is like to focus on how to use fundamental research to address the pain that people actually really made when they try to discover new materials. And the approach you are using, you can see all of these are like the modeling approaches. So we do the ab initio simulations, we do molecular dynamics, we do the regular CAFAD approach, we do the high throughput calculations, and also we do machine learning. Those are pretty much the main modeling approach we are using right now. So today I want to talk about 2 things, right? One is the main topic on the high entropy alloy. So we will talk what we have done, use the high throughput CAFAD approach, the ab initio calculations, and also the machine learning, right? There are some other research topics I will briefly introduce, give you an idea what my group actually are working on: SFC, SOEC, nanophase diagram, high entropy ceramics, those kind of things. Okay, so for high entropy alloy, this is a concept that people coined about less than 20 years. Yeah, essentially in the last 20 years. So this is a very young alloy family, and tons of research, right? In this field right now. It's a very hot topic. And high entropy alloy essentially is like you have 4 or 5 elements in your alloy, and you don't have just one primary elements there, right? So then those are like the high entropy alloy. So far there are several hundreds of high entropy alloy got discovered, physically discovered, right? And from this HP diagram, right, on this toughness and the yield strength, you will see high entropy alloy is somewhere here. This is like the existing high entropy alloy people discovered. Okay, so it has they have the very high toughness and also very high strength. So that is actually right perfect for a lot of challenging applications. So, but the real opportunity is not this, right? The real opportunity is like that, because as I said, this is new alloy, right? New alloy family. So there are still a lot of unknown region we haven't explored yet. So what I can say is probably we have explored less than 1% of the high entropy alloy so far, right? So it is really promising, and the reason people work a lot on this high entropy alloy is because of this new oval here. So it shows that we can further increase the toughness and the yield strength, and it is even possible that we can get the properties out of this map, right? So that is why we work on this. Okay, so but what is the challenge? The challenge is high entropy alloy by its definition itself. It has tons of compositions, right? And if you just use the traditional ways that you use to develop steel or develop like aluminum alloy, copper alloy, those kind of things, you will fail because there are so many different possibilities there. So it will take enormous time and effort to do that. So that is why the traditional trial and error approach will not work. And our approach is like we do high throughput calculations, right? And we can simulate what is happening for the phase stability at different temperatures. We can simulate what is happening on these long equiatomic compositions. And also we can simulate the mechanical properties, right? Okay, so with those, we can work with people working on experiments to quickly identify new alloys. All right, so this is these are the approaches my group actually are working right now for the high entropy alloy. One is this high throughput calculations to find the compositions that we want to working on. And the second one is about the DFT calculations, right? So, and this will be combined with the machine learning. So with this, we will mainly get the 0K elastic constant database. All right. Okay. We are not satisfied on these results, right? So we want to get something more, and this will be the third part. So the third part will be the temperature dependent elastic property predictions. Okay. So we will know the phase stability. We will know the elastic constants essentially at 0K. So based on this, we can do the screening to see what's the good composition we want to working on. And then we will check its elastic properties and elevated temperature. So then we will know its high temperature properties, right? So with that, then we can get good high entropy alloy compositions that we can recommend to people. Okay, so let's work on this one by one. So the first one is about these high throughput calculations. So this is the results we have for aluminum, chromium, cobalt, nickel, iron, 5-element system for the BCC and FCC, right? So instead of this traditional, simulation, we do, one simulations or two simulations, right? So here we do several thousands of simulations. And this is like the results we got like a couple of years ago, right? Now we can even do tens of thousands calculations pretty quickly. But no matter what, this shows that high throughput calculations actually can be very efficient for you to get what the stability range for BCC and FCC, right? Okay, and with those several thousands of compositions, we can do the screening, right, based on our criteria. So, for example, the color bar here shows the stability range for BCC, right, temperature range. So the red one means it has a very wide range that BCC is stable, and the y-axis is density, right? So based on this, we can get I call it a refractory alloy, and also with a very low density, right? When I say refractory, it means its melting temperature actually is very high, right? Okay, so with that, these are the compositions we have screening out, and especially there is a red one. This satisfy our needs, and after we got this composition, right? We did this one shot, right? These state calculations for this alloy, and it does show that this is a very good alloy. It will come with BCC and B2 phase, right? And has very high melting temperature. Okay, so with that, I hope I convinced you that these high throughput calculations actually can be very useful to quickly find the composition range you are looking for. Okay, so by solving these phase stabilities, right? So we still need to figure out the mechanical property. So how do we do that, right? So at first we want to know the 0K mechanical property. So this is what we have done, right? So we have developed these high throughput DFT calculations, right? And combined with the machine learning, then we can make prediction of the bulk modulars, shear modulars, those kind of things. So these are the supercells we have created, right, to do the calculations. And the formula here shows how we can calculate the bulk modulars and shear modulars. And of course, we will also use the machine learning, right? And then to figure out the modulars that we want to predict for all the composition range. So that is the key. So no matter which composition you are talking about, we will give you a map, essentially. Okay, so for example, right, for the DFT data, we get the bulk modulars, right, for different systems, and also we did the machine learning, right, and then we can figure out the whole composition range, right. So these are for two binary systems, right? Okay, and for the ternary systems, so these points are the compositions we have calculated, right? And then by doing the machine learning, we will generate the map, right? So that is what we will do for ternary. For quaternary, right? So we are limited by the three-dimensional space. So, but we figured out this is something we can do. We can simulate a space inside, right, close to ABCD. So what is happening? Okay. All right. Okay. So this is the DFT and machine learning, combined results to show you the bulk modulars for all the 10 ternary systems we have for this 5-element system, right? So the important thing is this is a whole map, right? So no matter which composition you're talking about, we have the value for you, right? And also this is the quaternary space I mentioned about, right? So for each quaternary system, we have bulk modulars, map for that. So with that, you can, pick what you want to get, right? And especially, for this quaternary space, right? So we zoom in, and this will show you the region, right? How the bulk modulars actually will change in this space. For the shear modulars, similarly, right? So we gave you the map for ternary and quaternaries. And this is a zoom in for the quaternary space, right? Okay. For entropy of formation, this is something thermodynamic property we're also interested, right? So our DFT can also provide you that. All right, okay, and you may challenge, you say, hey, all of these are simulation results, right? But the real value, we don't know, right? You may get some very good predictions, you may get some, totally wrong predictions, who knows, right? So we compare with experiment data that we can find from literature, right? Experiment data, of course, there are only limited experiment data available because each experiment data, come with quite a lot of funding support, right? So this is a bulk modulars. We found for pure elements, binary, ternary, and even quaternary system, right? So as you can see, the bulk modulars we got actually, right? The red one is from experiments. The black one from DFT, right? And the blue one come from the machine learning, right? So essentially our prediction has a very good agreement with the trend for comparing with experiment data, right? This is amazing. And our data actually slightly larger than the experiment data. That makes sense because for the real experiments, right? Real samples, you always come with some defects, those kind of things, right? That will hurt your, probably will hurt your bulk modulars a little bit, right? What do we predict is the ideal one? So based on this, we think, yeah, I mean, this is a very good agreement. And for the shear modulars, similarly, right? Our prediction has a very good agreement, right? And entropy of formation, essentially, the similar trend we have, right, with the experiment data. Okay, so overall, I hope that based on this, I convinced with you that our 0K database actually are also very reliable. And what will happen if we select a composition, we want to, what will happen at a high temperature, right? So we did our third-party simulations. So this is our simulation, right, for quaternary system, right, about the thermal expansion coefficient, and also the bulk modulars, shear modulars, Young's modulars. So as you can see, right, so it is, they are actually in the right range, right, and the trend is also the same, right? So with this, our simulation results can provide you a very good guidance, like what may happen at high temperatures. All right, so that's pretty much the main thing I want to cover today for the high entropy alloy, right? So we have done these kind of 3 different approaches to figure out the phase stability, figured out the 0K elastic constant database, and also the critical and the elevated temperature, right? Properties, right? And in the future, right, we will expand our database, right? So we will cover BCC, FCC, B2, L12, those kind of things. And we will expand the elements we want to consider. For example, right, we want to consider 20 elements. Then in that way, most of the alloy you are working on, we can get it covered. All right, okay, so the second part, I will talk about some other things, right? My group is working on. So one of these is this SOC, right? Solid oxide cells. So in the past, this is mainly about the SOFC, right? Fuel cell. And now it is more popular on these electrolyzer cells, right? All people do these reversible cells, right? So one cell can do both. Okay, so here it shows a very simple demonstration. What is happening on SOFC, right? So essentially you have air, right? Oxygen go this side, and it will go through the electrolytes, right? And then it will meet the hydrogen and form water. During this process, right, you will generate a lot of energy, right, and then you can produce electrical energy, right? So that is how you can generate electricity. So if you reverse this process, your input will be the electrical energy, and then you can have water, right, to be decomposed, right, from hydrogen and oxygen, right, like that. So then you can get the fuel, right? So that is why people are very interested on this topic, right? Okay, so but the problem for SFC and later on for SOEC is like for the oxygen electrode, people found a lot of degradation coming from that. All right. So for example, this is what's happening in SOFC, right? So your cathode can react with electrolytes. Your cathode will get in touch with air. In air, you have SO2, CO2, water vapor, chromium, all these things. So all these impurities actually will attack your cathode material, right? And then that will greatly reduce the performance. Okay, so that is what we call the long-term degradation. It's like your performance drop with operation time, right? Okay, so we have done a lot of work on this. So essentially, my group is probably the only group in the United States working on this thermodynamic, work for SFC or SOEC, right? So, typically, in each continent, you will have one research group working on this, right? In Japan, they have their research group on that. In Europe, they have a research group working on this, right? In the United States, my group is mainly taking charge of this. All right, okay, so to work on this, we mainly rely on this CAFAD plus approach. So this is a approach I coined. So traditionally, see what's happening. Oh, okay. Traditionally, we have the CAFAD approach, which is somewhere here, right? So you have the Gibbs energy based on the phase stability and the thermochemical data, right? For SFC, SOEC, what we have discovered is this different chemistry analysis will be very important. This is one additional, very critical input you will have, right? So in alloys, you don't have this at all. And what we found is we can quantitatively plot the Broward diagram, and we can make prediction of this traditional phase equilibrium, and also some additional things, right? One is the electrical conductivity, another is this thermochemical properties. All right, so for example, this is what we have done in the past, like develop the thermodynamic database. This is for Nathner or cobaltate, right? So you can see we have excellent map, excellent agreement with what people observed, right? Okay, and about the electrical conductivity, people know this theory a long time ago, right? As long as you know the energy barrier, right? And you know the carrier concentration, you should be able to get the conductivity coming out. And this is what we have simulated in the past for LSM, right? And as you can see, right, our simulation results has a excellent map, excellent agreement with the experimental data, right? And you can see we can generate this kind of a three-dimensional conductivity diagram, right? So it will show you what will happen for your conductivity if you change temperature, you change composition, you change oxygen partial pressure, all these things, right? So with this, you can pick the composition you want to work on, right? And you will know at your operation condition what will happen, right? Okay, another thing I want to talk is about our recent work on this high entropy ceramics. So because there are a lot of work on high entropy alloys. So people say, hey, in ceramics, we should also work on high entropy ceramics. So, but the issue is, right, 99% of the research market, they are still follow the high entropy alloy concept. So they just mix elements inside in ceramics, but they didn't pay attention what are actually mixing inside ceramics, right? When they are mixed together, because you have different chemistry, there, what you mix will not be elements. What you mix will be this kind of species. So we just did this kind of preliminary work, right, to show people, hey, what you are mixing is actually those species, and the behavior can be very different from what your intuition tell you. Okay, all right. So for example, right, so here we will have manganese 2+, 3+, 4+, and vacancy, right? They mix in the B side for LMO. This is very simple oxides. All right, and this is 3+, 4+, 2+, and this shows how they mix together, right? And this will show when they mix, in which condition, that is corresponding to, right? Oxygen partial pressure, temperature, and vacancy, also the thermodynamic properties, right? Entropy, enthalpy, and Gibbs energy. So with this, people can get a very good idea, what is happening. The last one I want to show will be the phase stability for the nanoparticles, right? Because nowadays we are all working on, nanomaterials, right? We always say, hey, I got some nano something, right? This, that. But how these nanoparticles behavior will change with different conditions, right? So how it will change with temperature, how it will change with composition, right? How it will change with particle size, right? So that is something a lot of people have found the difficulty to explain, right? So this is what we have done on the e-tron stabilized zirconium, and there are several different crystal structure there, right? Like a monoclinic, tetragonal, cubic, even amorphous phase happening there, right? And we can show with this, we can show you the boundary of those phase transformation, right? So then you will know if you change composition, you change your particle size, right? From 1 nano to 10 nano to 100 nano, right? If you have coarsening, right? When you increase temperature, right? What will happen? So this diagram will clearly show you this, and this has a very good agreement with what people observed by doing experiments. Okay, so those essentially are what I want to cover today, right? So one is on alloys, another is on ceramics. I hope that I have convinced you that thermodynamics actually play a very important role there. So if you haven't taken the thermodynamics course yet, right? So in B term, Professor Susan will talk about the advanced thermodynamics. So you are welcome to take that course. So I used to co-teach that course with Professor Susan, but this year the department make the arrangement that I need to teach some undergraduate thermodynamic course for mechanical engineering students, right? And also in C term, after you actually take this B term thermodynamics course, C term I will talk about this advanced the computational thermodynamics. So then you will get a chance to learn how to adopt the idea you got from the traditional thermodynamics, right? And you combine the computational approach together, right, to plot the phase diagram, those kind of things. So that is that. And also in D term, I will also talk about how to combine the computational thermodynamics, the DFT with machine learning. So you are also welcome to take that course, right? That will be the what's happening in D term. And also research-wise, if some master students are interested, no matter high entropy alloy or SOEC, right? This electrolysis cells. I have openings for students. So if you are interested, you can contact with me, and I will give you opportunity to work with my current PhD students. And if you work with them for several months, that you demonstrate that you are a serious researcher, right? And then I can convert you, get into a PhD program in fall 2022. All right. Okay, so that's pretty much I want to cover. So thank you everyone. Happy thermodynamics. Any questions?
I have a few questions for Professor Zhong, but those are more personal and they can wait until after everyone else is gone.
Okay, so we can chat, offline if it is not related to the topic I talk about, right? But if you have some technical question on the content that I cover, yeah, feel free to shoot now.
We'll take any questions now. So.
Hi, I was wondering if you'd say.
Hi, Jason.
How long?
Long time.
Hi, I'm doing good. Can you explain how long do these simulations normally take?
Depends, right? Depends. So if you do this typical cover, calculation, that can be very quickly, right? I'm not sure which topic you are, working on right now. But for typical covered work, we are talking about several minutes to half an hour, something like that, right? But if you do this high throughput covered calculations, we're talking about 1 day, 2 days, or a week, right? Because we're talking about thousands or tens of thousands calculations. And if you're talking about the DFT calculations, it varies, right? The simple calculation can be done, in a minute. So complicated one, is Yao is all right. And if you are talking about some complicated ones, that may take a couple of weeks. Okay, so that is the DFT calculations. Machine learning actually can be pretty quick, especially based on what we have so far, right? But if the machine learning is combined with some other simulation, for example, we are combining our machine learning with the molecular dynamics, right? So the molecular dynamics itself will take a while. That will cost a lot of time, right? Because we need to do one molecular dynamics simulations and then go back to do the machine learning, right? And then back and forth. So in total, that will actually, take a day or two, something like that, right? Okay, so that's pretty much the idea of how long one specific, calculations, you need to get it done. For the, for example, for the high throughput DFT calculations we have done for this 5-atom system, that actually takes several months because we're calculating a lot of different compositions, right? Okay, so what my group is working on is, because our target is trying to develop a 20-element database for FCC, BCC, and some other order phases. So we are talking about a lot of compositions. So I have a student actually, working on this. We're trying to make everything automatic, right? So then, let computer run for several months, and then we go to pick the data we need, right, like that. So a lot of exciting things going on right now. Yeah. Does that answer your question, Jason?
Yeah, thank you.
Yeah, thank you.
All right, are there other questions?
Hello.
I sent a
Um,
private message to you, Zhong, with a question, but I'll just wait for him to get back to me.
Okay.
Okay, all right.
yeah, Professor Zhong, thank you so much for that wonderful presentation. So the question I want to ask is that if you want to do the DFT calculations, so how do you determine the, for instance, you have different compositions and you probably want to know the equilibrium structures, like you want to know the equilibrium atomic positions and all that before you go ahead with the calculations. So how do you determine that?
Yeah, that's that's a very good question. May I have your name?
Read one.
Oh, read one. Okay, yeah, because I only see your email address. I cannot tell. So you are currently a PhD student or master student here?
PhD student.
Okay. So you have some research related to DFT?
Yeah.
Oh, all right. Okay. So there are several things you need to consider, right? So for the typical DFT calculations, we're talking about the 0K, right? So we are talking about the phase stability and the 0K, not the elevated temperature, right? What you can do is at first, based on experiments, right? So people must talk about, what are the stable structures. And also you can get some hint from the covered approach, right? That will also give you a hint what may happen at a 0K. And another thing is there are many ways you can do, right? And another way is you can consider all the crystal structures that this material probably can have, and then you calculate all of those. The one come with the lowest energy will be the stable one. Yeah. Yeah. Okay.
Yeah.
Yeah. So for example, if you have a pure element, right? So essentially, most of those are either BCC, FCC, or HCP, right? So most of those are one of those three, and then you just calculate these three, right? And then which one gave you the lowest energy? Then that is a stable structure.
Okay. Yeah. Thank you.
Yeah, sure.
Yeah.
Right. Well, not seeing other raised hands. I have a quick question for you.
Sure.
So I was looking at your visualization of the three-dimensional visualization of the conductivity as a function of the other parameters, the pressure and other things. And it seems like there are some big trends that stick out. Like it seems to be that there are two different regimes. One where the conductivity is a function of yes, looking at the 3D plot. There we go. Yes. One where the conductivity is clearly a function of some ratio of the log of oxygen partial pressure to the temperature.
Yeah.
And then there's another regime where it kind of levels off and then it increases again. But in addition, it looks like this partial pressure versus temperature has some kind of curvature to it in that rainbow region. I'm wondering.
Yeah, essentially it is here.
Okay. Yeah. So I was wondering what your interpretation of that, some of these different parts of these different regimes are for that that graph.
Yeah. So so as I mentioned, right? So here, this is the electronic conductivity. So this is mainly determined by the manganese. I think this is manganese 4 plus, right? Manganese 4 plus composition and the concentration. So how it will change with oxygen partial pressure. So essentially, this is everything here is determined by the defect chemistry. Okay, so this manganese concentration is changing, right, with oxygen partial pressure. So then that is why the conductivity will also change, right? Will also increase with oxygen partial pressure.
Okay, I see. So so the total electronic and ionic conductivity that you're showing here.
Yeah, because this is an electron hole mechanism.
Right. Right. Okay.
Yeah. Yeah.
All right. Thank you.
Yeah. Sure.
All right. Are there other questions for our speaker? All right. Well, not seeing any. I think we can thank our speaker. So thanks very much, Professor Zhong. It's good to see you on Zoom, even though you're right next door and in the next office.
Yeah.
Terrific. Great. Well, thanks for a very interesting talk on high entropy alloys and on the defect chemistry and fuel cell cathode materials. Really appreciate it.
Yeah. Sure. Definitely. Definitely.
And thanks everyone for joining us.
Mhm.
Okay, so you've seen this is on YouTube. I'm also going to post the recording onto the Canvas for all of you in the seminar, registered for the seminar. So,
yeah.
Thank you very much.
Cool. All right. Okay. Thank you. Thank you, everyone. All right. Okay. Have a good day.
Bye.
Yeah.
Do you mind if I stay on to ask my question?
Oh, sure.
Then I will work with you later offline. Yeah. Don't worry.
Okay, but did you?
It's up to the two of you. We can keep this open for a few minutes if you like.
I think he's gone.
Oh, okay. All right. Okay. All right. Thank you again.